Is Dr. Amy Heffernan, and she's a technical specialist with Eurofins Environment Testing Australia and New Zealand, and is currently based in Brisbane. Amy has a PhD in environmental chemistry from the University of Queensland and has nearly 15 years experience in analytical and environmental chemistry. She specialises in liquid chromatography, including high-resolution techniques for, liquid chromatography mass spectrometry, including high-resolution techniques for trace-level environmental monitoring. Her research portfolio includes analysis of contaminants of emerging concern, which includes PFAS, organophophate, flame retardants, brominated flame retardants, phthalates, and plasticizers. And much of this research is being used to inform national policy. Thank you very much, Amy. So we can see your screen at the moment, but I can't hear you. Rightio. There we go, Amy. I can hear you now.
I just need someone the host to enable my video.
Yeah. Try now.
Fabulous. Hi, everyone. Thanks for that, Brad. Thanks for the introduction and the invitation to talk with everyone today. It's actually been rather perfect, I would say. The talks we've heard this morning have been the perfect setup for my talk. It's almost like we planned it, even though we didn't. So today I'm going to be talking to you about some work that I did as part of my PhD project and early postdoctoral research. And that's to do with human exposure to pseudo-persistent chemical contaminants in the environment. So to explain the idea of pseudo-persistence, I guess we really need to start by talking about the traditional models of assessing exposure, and that's the PBT model, or persistent bioaccumulative and toxic substances. And probably the best example of these are the persistent organic pollutants, such as those that are regulated under the Stockholm Convention. And if I just pick out some of the chemical characteristics of chemicals that typically fall under this PBT model, we're generally looking at compounds with a long half-life in the realm of years, and that's for both environmental degradation as well as elimination from the human body. They're often lipophilic, which is related to their half-life. Sometimes we're looking at bioaccumulation and biomagnification, and specifically for POPs capable of long-range transport. So if we move now to this idea of pseudo-persistence, so what does this actually mean? I'm going to start with an example, and in this case it's pharmaceuticals and personal care products. And if we compare the chemical characteristics, one of the definitions of a compound that's pseudo-persistent is when the time to exposure is less than the time to degradation. And I'm going to come back and revisit this idea later. But conversely to PBT chemicals, pseudo-persistent compounds are often polar and water-soluble. They have a short half-life in the realm of hours to days rather than years. And as a result of these characteristics, they readily undergo transformation and degradation processes, again, in the human body as well as in the environment. So I'm going to take you now to a specific example of a pseudo-persistent compound, and that is bisphenol A, or BPA. So thank you to Gabby for mentioning it in your talk earlier today. BPA is a plasticizer. It's used specifically in polycarbonate plastics and in epoxy resins, which are used to line canned foods, for example. So both these types of materials are used extensively in food containers, in baby bottles and can coatings. And one of the another sort of different application, I suppose, is in the thermal paper used for receipts. So BPA has been associated with a range of adverse health outcomes on the reproductive system, cancer, obesity and type 2 diabetes, and behavioural effects. It's quite a controversial field, so I'm not going to delve any further into it. But what I did want to raise is that BPA is widely recognised as being an endocrine disrupting chemical, and we've already heard a bit about these today. So talking specifically still about BPA, you can see on the right hand side here the chemical structure of BPA, and above it here is estradiol, the major female sex hormone, and there are some structural similarities between these two compounds, and this results in BPA having estrogenic potential. It's between 1,000 and 10,000 times weaker than estradiol. In the human body, it can compete with endogenous estrogens for binding, and also has been noted to have anti-androgenic properties. If we zoom out now to think about endocrine disrupting chemicals generally, there is this sort of global phenomenon that's been discussed over the last, over recent decades, of precocious puberty, that is puberty onset occurring earlier as time goes on. We also heard earlier today about a global decline in sperm quality, and we know that endocrine disrupting chemicals can have multi-generational effects. So what becomes really important when looking at any sort of chemical exposures, but particularly endocrine disrupting compounds, is critical windows of exposure. So over the course of a human lifetime, there are 3 critical windows. The first is pregnancy and in utero exposures. The second is infancy, and the third is adolescence. Now, the reason, so the work that I did focused specifically on infancy, so that's from sort of birth to up to 5 years of age. And the reason why this is particularly important is that children in this, or infants in this age range, have different behaviour. They have different exposures and different sensitivity, and so that really changes the way that we characterise exposures for infants and the impacts it might have. So if we can compare this specifically to a traditional toxicological study, these are normally done either in rodents, or if they are done in humans, it's done on adults, and we're looking at acute high chemical doses, not chronic low dose. Now, as you can imagine, it can be quite difficult to work with infants. So there are specific challenges around informed consent, sampling procedures. You can't ask a baby to give you a urine sample in a urine cup, for example, and typically we are working with very limited sample volumes. And because I don't like to do anything by halves, I thought I would combine this specific challenge of working with infants with an analytical challenge. And the analytical side of it comes from Bisphenol A and plasticizers in general being ubiquitous contaminants. So it becomes really important to try and eliminate any potential contamination sources from your analytical pathway. So in my case, I used, what we have here is an ISO 5.6 clean room, which is basically a big metal box with no plastic components within it at all. And we use this alongside some other techniques like a liquid handling for large volume injection. I used online solid phase extraction and another liquid handler that's not shown here, really to just completely eliminate any human contact with the sample as much as practicable. And yet, even with all of these measures in place, we still get a reasonably robust signal from the blank. So this is, I just point this out because it really is a significant challenge. And so I have published this work specifically, and the reason I mention this paper is I hope that it is going to be of use to the field more broadly, and it's all about the considerations for sampling and storage of for human biomonitoring studies, and it's aimed at a clinical audience. And I have to acknowledge Dr. Maria Jose Gomez Ramos, who was really instrumental in this particular part of the work. All right, so now that I've got my samples and I have my analytical method, let's start looking at the actual bisphenol A data. So one of the strategies to address the sample collection challenges for infants was to use a pooling strategy. So this is where you take the same volume of sample from a number of individuals. In my case, it was 7, and we combine these samples to create a composite. And by doing this, I was able to take 790 individual specimens and combine them into 67 individual pools. And this gives data that looks like this. So this is bisphenol A urinary concentration versus age. And comparing that to the literature, there was really very little comparative data available because of the challenges that I've outlined previously. But the range in Australian infants was pretty much spot on with what we were seeing in other parts of the world, and that's in the low nanogram per mil range. You can see that I do have older age groups included here for comparative purposes, and so this work was used, the data from bisphenol A as well as a host of other compounds formed part of the Australian National Biomonitoring Program. And so this was the first year that a urine monitoring program was included in that. So we have here a comparison of our infants from 0 to 5 with older adults. And we started to think, we already know that infants are different from a toxicological perspective, but what about physiological differences as well? And when we start talking about urine data as opposed to blood, for example, it becomes really important to think about how much urine a person produces per day. Blood is generally a fixed volume, unless you've got some serious problems, whereas urine can really fluctuate. So I gathered up all of the available data that I could find on urine output during early life and created a model here. And you can see that particularly in the first few years of life, an infant is producing a much greater volume of urine compared to around the age of 10 to 15 years, at which point it just plateaus, even for adults. So what happens when you apply the urinary model to the BPA concentration data, and we can convert urinary concentration to mass excreted and from there to estimate exposure, is that suddenly we now actually have a significant effect of BPA exposure with age. So we have higher exposure here in infants compared with older adults. And so I just want to revisit the idea here of pseudo-persistence by looking at a couple of theoretical exposure profiles. So if we look at a persistent compound, and you could take your pick, let's say one of the PCBs, for example. Generally, we have a profile that looks like this, where we might have one particular exposure, and then that compound is persistent, so it stays in the body for a long time. The x-axis here is in the realm of years, and generally we have some information about the half-life or degradation rate of these compounds because they've been around for a very long time. Now, conversely, if we look at a pseudo-persistent compound like bisphenol A, instead we have repeated exposures, and here the x-axis is in the units is in days. So for BPA, we know that the major exposure pathway is actually food source. So you can imagine that each of these exposure events is when you eat something out of a plastic container, for example. So while all of these concentrations will even out to produce some sort of urinary average, the time at which you take the sample actually has a really huge impact for these pseudo-persistent compounds. And that's completely different to persistent compounds. So I've talked so far about bisphenol A, but I wanted to just show a couple of examples of other compounds that also fall into this pseudo-persistent under this sort of umbrella. And that's here we have N-propylparaben on the left and benzophenone 3. So parabens are used a lot in cosmetics as preservatives, and benzophenone 3 is a UV filter, so it's used, for example, in sunscreens. And if you pay attention now to the y-axis, you can see that these are both on a log scale. Each of these numbers 1 through 8 is an individual participant in this study. And we have a huge variation within a single individual, sometimes over 2 to 3 or even more orders of magnitude for these particular compounds. And here on the right-hand side, I should say this is not my work, this is work by Dr. Holger Koch from the German Occupational Medicine Center in Germany. The benzophenone 3 data that we're looking at here, this is just a single individual who was monitored over a number of days, collecting every single urine sample, and you can see how wildly the urinary concentration of this BP3 really changed. And in this particular case, it was because she was using a hand wash that happened to contain this compound. So every time she washed her hands, she was re-exposing herself to this compound. So why do I bring this up? Because it means that the timing of sample collection is really crucial. So despite the challenges that I outlined of working with children, I did do one study that collected individual samples from children who were aged between 2 and 3 years of age. So they collected, the parents were instructed to collect 4 urine samples over 48 hours. So from that, we can obviously calculate the mean. But what the purpose of this study was really to characterize the variability, both within person and between people. And to do that, we can calculate what's called the intra-class correlation coefficient, which is the ratio of these two values. And here we have a value of 0.51, which means that this variation is more or less equal between the two. And what this tells us is that it's quite different to what we normally see in adults. So normally the ICC is a lower value, typically between 0.1 and 0.3. And the hypothesis is that infants have different kinetics, so slower elimination of these compounds. They're more frequently exposed. For example, their meal times might be highly regulated throughout the day, and also they're eating a reasonably homogeneous diet with less day-to-day variation. So the major takeaway being that we have less within individual variation in children compared with adults. So taking this one step further, we have our ICC value now. So let's have a look at how many samples are needed to predict the true mean and how many samples are needed to correctly categorize each sample in terms of their exposure. So I take all of the data from the previous study and scrunch it all up into one, and then divide all of those exposures into 3 categories, high, moderate, and low, and then apply a bootstrapping exercise to assess the relative reduction in accuracy in exposure classification, depending on if we're using, if we're using 1, 2, 3, or 4 samples. And so what this data tells us is that if we use just 1 sample, we have a high correlation to the true mean, and we are correctly categorizing exposure in roughly 70% of the time. This is my final slide. I'm just watching my timer with one eye. I wanted to finish up by really taking a zoomed out view of human exposure, in this case to BPA, but also more broadly, and talk about France for a moment. So in early 2011, the European Union banned the use of BPA in baby bottles as part of the precautionary principle. Curiously, in 2015, France extended this ban to all other plastic products, both those used by children as well as those used by adults, and this include canned foods. Now, as a result, you can imagine that the plastics industry was not very happy with this. And that I just have this little grab quote here from Plastics Europe, that the 2015 ban caused a distortion of the internal and international market. It increased uncertainty for all, with no safety benefit for consumers. And the reason for this is that canned goods that had BPA in the epoxy resin linings could no longer be imported into France. But then come September 2015, this rule was overturned. So what it meant is that French products can be exported using BPA resin-lined cans, but the import ban remains. So it's a bit of a curious dichotomy there by the French government, but it makes you stop and think, I believe, about, you know, what is the purpose of these sorts of chemicals in our lives. And for BPA, without the ability to properly preserve food, such as by canning, what we end up with is basically botulism. And I'm talking about the kind that lands you in hospital, not the kind that keeps us looking smooth and wrinkle-free. So to sum up, exposure to pseudo-persistent chemicals such as BPA can still be significant, and we know that Australian infants are exposed to BPA, and these levels are consistent with previous studies and less than the tolerable daily intake that has been set. There are sampling and analytical challenges that exist for compounds that are both highly variable and also ubiquitous. And finally, that there are real-world considerations for chemical regulation and substitution. And what I've put here are some of the BPA substitutes, such as BPF and BPS, which you can see are almost identical in shape to both BPA and estradiol. So we can imagine they'll have the same effect. And with that, I'd just like to acknowledge my supervisory team for this work, and happy to take any questions.